In this presentation, I am going to explain previous GATE questions and answers for the year 2022. And the topic covered is power electronics. Let us see the first question, that is 2022 GATE question, and that carries 1 mark. First question is, a charger supplies 100 watts at 20 volt for charging the battery of a laptop. The power devices used in this converter inside the charger operates at a switching frequency of 200 kilohertz. Which power device is best suited for this purpose? That is the question, and the answer options are A. Thyristor, B. MOSFET, C. BJT, and D. IGBT. And this is operating at 200 kilohertz, and of course the power is medium power. Therefore, for a high switching frequency and low voltage operation, the best suitable device is MOSFET. And the correct answer is the option B. And if you look into the different devices as such, MOSFET can be operated for high frequency medium power application, and IGBT can be used for high speed and high power application, and BJT, bipolar junction transistors, can be used for that capable of handling high current and voltage and has slower switching speed. And thyristors are high power and can carry high power but lower switching speed. For these are the these are the characteristics of the different devices, where it can, based on that, we can use the different applications. And in this one, the correct answer is the option B, MOSFET. Now let us see the second problem of the 2022 GATE question, and that carries 1 mark. A single phase full bridge diode rectifier feeds a resistive load of 50 ohm from a 200 volt 50 Hz single phase AC supply. If the diodes are ideal, then the active power in watts drawn by the load is, that is, round off to the nearest integer. That is to be round to the nearest integer. Therefore, this is a single phase diode bridge rectifier circuit, and this is a resistive load like 50 ohms. And here the input voltage equal to 200 volt 50 Hz. And this is just, if this is the input, and during the positive half cycle, as you know, that these two diodes are conducting, and then you will be getting a voltage that is similar to that 0 to pi radians, same as this one. And of course, the negative half cycle of the input, these two diodes are conducting, and here the path is like this one. Again, the voltage across the resistor having the same polarity with plus here and minus here, or this is the output voltage. So this is the output voltage waveform across the load resistor, and this is the input voltage at the input of the uncontrolled rectifier, bridge rectifier. Now coming to that one, load resistor is 50 ohm, and the supply voltage is 200 volts RMS value, and the frequency equal to 50 Hz. And the peak value of the supply voltage, of course, root 2 times 200, which is equal to 282.84 volt. And the RMS value of the load voltage, the RMS value of the load voltage is same as the RMS value of the input voltage. Therefore, here it is same as input voltage RMS value, which is equal to the same 200 volts. Therefore, this is the RMS value of the voltage, output voltage 200 volts, and the resistor equal to 50 ohm. Therefore, the power dissipated, that is the power drawn from the active power drawn in watts, that is drawn by the load, is given by V squared by R, or VRMS squared by R, which is equal to 200 square divided by 50, and that's equal to 800 watt. That is the answer. Now let us see the third question of 2022 GATE question, and that also carries 1 mark. Third question is, the voltage of the output of an AC DC rectifier is given by Vt equal to 230 root 2 sine omega t, where omega equal to 2 pi into 50 radians per second. And the input current drawn by the rectifier is given by, the input current is not sinusoidal, that apart from the fundamental, there are third harmonic and fifth harmonic. And It is given by 10 sine omega t minus pi by 3 plus 4 sine 3 omega t minus pi by 6 plus 3 sine 5 omega t minus pi by 3. Therefore, this is the current at the input side, and of course, this is the voltage. Therefore, here, as we have seen, this is the control rectifier circuit, as we can see that, and there are 4 SCRs, and during the positive half cycle, T1 and of course the T3, of course T1 and T2 and negative half cycle T3 and T4 are triggered, and this is a single phase supply, and this is the load as such. And here the question is that the input power factor round to the 2 decimal in the, what is the power factor at the input side? Therefore, coming to that one, the source voltage is given by 230 into root 2, that is the maximum value into sin omega t. Therefore, and similarly, the current waveform is also shown here, which is, of course, the equation is given here. So fundamental, this is the third harmonic, and this is the fifth harmonic. And the fundamental power, normally to find out the, of course, here the question is that power factor. To find out the input power factor, what method is that? First, you will be calculating what is the fundamental real power. How that is to be supplied from the source. What is the fundamental real power or fundamental active power? Second stage is that we'll be calculating what is the apparent power at the input side. And the ratio of the fundamental active or real power to the apparent power is the power factor. Therefore, in this case, you can see that one fundamental input real power, that is fundamental real power, that is P1, it's notated, which is equal to the RMS value of the voltage, 230 root 2 divided by root 2, that into what is the RMS value of the fundamental. 10 is the maximum value, therefore 10 by root 2, and cosine of the angle between the voltage and fundamental current, that is pi by 3. Therefore, that substitute pi by 3. Then you will be getting 813.17 watts. This is the fundamental active or real power that is to be supplied from the source. Next, we have to calculate what is the RMS value of the total current. This is the total current, includes the fundamental, third harmonic and fifth harmonic. What is the RMS value of the total current? Which is equal to square root of RMS value of the fundamental, 10 by root 2 whole square, plus RMS value of the third harmonic, which is equal to 4 by root 2 whole square, the RMS value of the fifth harmonic, which is equal to 3 by root 2 whole square, under square root. We'll be getting it is equal to 7.905 amperes. Therefore, this is the RMS value of the total current at the input side, and the RMS value of the voltage is equal to 230. Then apparent power at the input side, that is to be supplied from the source as such, it is equal to 230, which is equal to the RMS value of the source voltage and the RMS value of the source current, and 230 into what is the RMS value of the source current, which is equal to 7.905, and we'll be getting 1818.15 volts. 1818.15 volt is the, this is the apparent power to be supplied from the source. Then the power factor of the input side is equal to the active or real power that to be supplied from the source divided by this apparent power, and that will be getting, it is equal to P1 by S, which is equal to 813.17 divided by 1818.15, which is equal to 0.45. Therefore, the input power factor of this answer is 0.45. Of course, this is a lagging power factor. It is minus pi, but that's why it's a lagging power factor. Now, let us see the fourth problem of 2022 gate question that carry 2 marks. Consider an ideal full bridge single phase AC or DC to AC inverter with DC bus voltage of 1000 volts, and the inverter output voltage that is shown here, shown below, is obtained when diagonal switches of the inverters are switched with a 50% duty cycle, or this is during the positive half cycle and this is the negative half cycle as such. For 50% for equal length, equal time period. The inverter feeds the load with a sinusoidal current. Therefore, the output, this is being supplied to a load that and the load current is sinusoidal, that is given this one, 10 sin omega t minus pi by 3, where omega equal to 2 pi by t. Therefore, this is the load current and this is the load voltage. Now, the active power, what is the active power, in watts delivered to the load? That is the question. What is the active power delivered to the load? That is to be round off to the nearest integer. Okay. Therefore, this is the inverter output voltage, and this is given by the load current. Now, looking into this voltage as such here, if you take the Fourier, and if you do the Fourier analysis of that one, that if you see that one, this is having a odd symmetry as well as half of symmetry, meaning that Ft equal to minus of F minus T. That's called the odd symmetry. Similarly, half of symmetry also there. This waveform has a half of symmetry like ft equal to minus of ft plus t by 2. These two properties are there for this verb form, and in that case we can see that one here a naught, that is the Fourier constant a naught, that is will be equal to 0. Similarly, the Fourier constant an also will be equal to 0. Only bn will be present if you have these type of two properties like half-wave symmetry as well as odd symmetry, that is this verb form is having. Therefore, from this one you can find out what is only bn is present, or bn equal to 4 by 2 pi integral 0 to pi v sin omega t d omega t, or if you integrate we can say 4v by 2 pi n cos omega t minus cos omega t from 0 to cos pi, it will be getting 4v by n pi. Therefore, this is the bn value, and for the to get fundamental constant like bn, actually here since an equal to 0, here the maximum value will become equal to bn, which is equal to 4 by fundamental quantity maximum value equal to 4 by pi, because n equal to 1. In that case, the maximum value of the fundamental output voltage is given by 4v by pi. Substituting this one, n equal to 1, it is equal to 4 into DC bus voltage equal to 1000, 4 into 1000 divided by pi, or 1273.24 volt is the maximum value of the fundamental. And the RMS value of the fundamental is given by the maximum value divided by root 2, which is equal to 900 watts. Therefore, the inverter output maximum value and RMS value is given by 900 watts. Now, continuing the same problem, here the RMS value of the fundamental we already calculated is equal to 900 watts. And of course, the current is shown here 10 sin omega t minus pi by 3. So this is having, the phase angle shift is there of pi by 3 radian. And this is the fundamental output voltage, and then RMS value of the fundamental output current. If you see the RMS value of the fundamental output current is equal to, this is equal to 10 by root 2, which is equal to 7.07 amperes. You know what, the fundamental voltage also known, RMS value, and fundamental current also known. And of course the fundamental power factor is also, it is equal to pi by 3. Fundamental power factor angle is pi by 3, or it is equal to pi by 3, or the power factor equal to cos pi by 3 or cos 60. Therefore, the active power that is supplied to the source is given by RMS value of the voltage and RMS value of the current, RMS value of the, of course, fundamental voltage and RMS value of the current, and the cosine of this angle, or it is equal to 900 into 7.07 into cos 60, which is equal to 3181.5 or 3182 watt. That is can be approximated to 382 watts. And of course here the basic equation to be remembered here is that if for the square wave with a half wave and odd symmetry, you can remember that one, an and a naught both are 0, only bn will be present, and based on that one the output voltage can be written as sigma a, and that too here only first, third, fifth, only odd harmonics are present for bn, or in that case sigma 1, 3, 5 like that one, it is equal to 4v by n pi into sin n omega t. Therefore, if you remember this equation, you can calculate all these parameters. Therefore, this answer is 3182 watts. That is the active power delivered to the load. Now let us see the fifth problem of 2022 gate question, and that carry 2 marks. For the ideal AC DC rectifier circuit shown in the figure below, the load current magnitude is at 15 amperes. The load current magnitude is 15 amperes, and the ripple free also is ripple free. And the thyristors are fired with a delay angle of 45 degree. These thyristors, these are two thyristors and diodes. The thyristors are fired at an angle of 45 degrees, 45. And the amplitude of the fundamental component of the source current in ampere is that much. Therefore, if you see looking to the circuit here, that is during the positive half cycle of the input, these can be, these devices or T1 can be triggered, and these two will be conducting. And during the negative half cycle, this one and these two things can be, this is forward bias, and these two, thyristor and this diodes are conducting. Now, if you see that one, this is the input voltage, and during the firing angle of 45 degree here, when it is fired, T1 and of course here D1s are conducting. Therefore, the path is like this one, it is returning back. Therefore, here plus and here minus, you'll be getting a voltage same as the similar to the input voltage. But at pi radians to pi plus alpha radian, you can see that one, this is of course switched off, and this is not yet switched on. Also here These two are, therefore here, here T1, D2 are conducting. T1 and D2 are conducting here. T1, this is here. T1 and D2 are conducting in this course, of course, and here, here the voltage, output voltage equal to 0. And again, T2 and D2 are conducting here, and then output voltage is, in that case, again the path is like this one, and here plus and minus, therefore we will be getting positive voltage only. Therefore, this is the output voltage, and this is the input voltage, and the load current is marked as, this is the load current, it's a constant load current. And if you see the input side current, that is when T1 and D1 are conducting, then the current will be in this direction, therefore we will begin a positive current. When T2 and D2 are conducting, we can see that one, the path is from this one, and the path is current, it is current direction is opposite, therefore you get a negative current. Therefore this is the current at the input side of the, the AC to DC rectifier, and this is the load current, and this is the output voltage, and this is the input voltage. And if you look into this one, again this has got an odd symmetry like Ft equal to minus Ft plus T by 2. If there is an odd symmetry, of course A0 will be equal to 0, the DC component will be 0, or the Fourier constant A0 is equal to 0. And we can then, here we can calculate what is the Fourier component corresponding to the fundamental A1, similarly corresponding to the B1 also, that's also corresponding to fundamental. A1, B1 can be calculated, and then we will be getting the corresponding equation, that is we are taking the Fourier analysis of this one, and we are taking the Fourier constant for corresponding to the fundamental. A1 equal to, that is written here, 4 by 2 pi integral alpha 2 pi I naught cos omega t dt, d omega t, which is equal to 2 I naught by pi sin alpha. Similarly, B1 also can be derived, the Fourier constant for corresponding to the fundamental, which is equal to 2 I naught by pi into 1 plus cos alpha. That's the first step. We will be calculating what is the Fourier constant A1 and B1 corresponding to the fundamental. Once we get A1 and B1, that is 2 I naught by pi sin alpha and 2 I naught, pi sin alpha, not 2 I naught divided by pi into 1 plus cos alpha. Once you get A1 and B1, as you know that when the maximum value of the fundamental is given by square root of A1 square plus B1 square. Square root of A1 square plus B1 square. Maximum value, root of A1 square plus B1 square. Therefore, we are taking square root of this one square plus this square, or we'll be getting, it is equal to 4 I naught by pi into square root of cos square alpha by 2. Then RMS value of this one is given. This is the maximum value. RMS value equal to divide by root 2. Therefore, 4 I naught divided by root 2 pi. Of course, that will be the RMS value. But the question is here, that is the maximum value of the fundamental is calculated, and here that is substituted here, 4 I naught divided by pi into cos squared alpha by, corresponding to the firing angle of 45 degree. The maximum value of the fundamental is the question. Therefore, we have to substitute in this equation, and it is 4 I naught divided by pi, that is 4 into 15 divided by pi into square root of cos squared 45 divided by 2, which is equal to 17.64 amperes. That is the maximum value of the fundamental at the input side. Of course, RMS value equal to divided by root 2. Therefore, to remember in this type of, the basic equation is that maximum fundamental source current in a single phase semi-converter with constant load current and firing angle. You just rather than deriving this one, you just remember this equation. 4 I naught divided by pi into root of cos squared alpha by 2, where alpha is the firing angle. For example, if alpha equal to 60 degree, then 4 I naught divided by pi into square root of cos square 60 by 2, like that. For you, please remember this equation so that no need of deriving like this one. Now let us see the sixth problem, that is 2022 gate question, and that carry 2 marks. A three-phase grid connected voltage source converter with DC link voltage of 1000 volts is switched using sinusoidal pulse width modulation, sines PWM technique. And if the grid voltage, if the grid phase current is 10 amperes and the three-phase complex power supplied by the converter is given by minus 4000 minus J3000, that is the apparent power, actually it is a volt ampere, and then the modulation index of the sinusoidal PWM is what? That is a round off to the 2 decimal place. That is the question. We have to find out the amplitude modulation index MA corresponding to this much power as such, and this is link voltage, or that is equal to 1000. volts. Now, if you look into the Fourier, the sinusoidal PWM, there are two waveforms. One we call the modulating signal. That's also called reference signal. That is a low frequency sinusoidal signal that is being compared with a high frequency triangular signal. That is the switching frequency that's correspond to the switching frequency. Therefore, that triangular signal, the ratio of the maximum magnitude of the modulating signal or the reference signal to the maximum magnitude of the triangular signal, that we call it as modulation index MA, or amplitude modulation index MA. Maximum value of the, this is also called control voltage, or that's called also modulating voltage, that divided by the maximum magnitude of the triangular signal, that is called, maximum magnitude, that is called VTR, that's called the MA. Yes, therefore based on that one, the switching is like when this is more than this one, we'll be getting here. If this is more than triangular, we'll be getting plus voltage. If it is less, it is negative voltage. Therefore, this is the output voltage, and the fundamental of this voltage will be in phase to the modulating signal. The fundamental output voltage of the inverter will be in phase to the modulating signal, and the magnitude is being related. That is, we are seeing that fundamental phase voltage of the three-phase sine PWM, that is given by fundamental phase voltage is maximum value of fundamental phase voltage is given by, which is, this is a maximum value, which is equal to MA into VDC by 2 into sine omega t. That is the phase voltage maximum value. MA into the DC bus voltage divided by 2 into, that is the equation. And this is the, actually this maximum magnitude is MA into VDC by 2. Therefore, the maximum value of the phase voltage is given by MA into VDC DC bus voltage, and maximum value of the line voltage is given by, of course, into root 3 comes MA into root 3 VDC divided by 2. Therefore, this is the maximum value of the line voltage. Now, it is given that apparent power is given as minus 4000 minus J 3000 volt amperes. S equal to minus 4000 minus J 3000 volt amperes. And that is equal to, that apparent power can be equated as, if that is equal to root 3 into max, of course, the root 3 into the RMS value of the line voltage. That is VL1 RMS value, that is equal to RMS value, and that into the line current, that is line current is given as 10 amperes. That is equal to the apparent power S, voltage into current. Of course, 3 phase, it is equal to root 3. Therefore, here we can see that when VDC equal to 1000 and IL equal to 10 amperes, substituting this equation, root 3 into and here VL1 max equal to MA into root 3 VDC by 2. For MA into root 3 VDC divided by 2 into what the 10 amp, that is also RMS value only, that is equal to 10, that is equal to the apparent power. Apparent power means this is the real power and this is the reactive power. For apparent power equal to root of P square plus Q square. S equal to root of P square plus Q square. Root of 4000 square plus 3000. Here 4000 square plus 3000 square, which is equal to, this root of 3000 square plus 4000 square, and we can get 5000. And based on that one, root 3 into MA into root 3 into MA into root 3 VDC 1000 divided by 2 into, of course, here the root 2, we have to take it as MA into root 3 VDC by 2 into the RMS value we have to take. That is why we are taking divided by root 2 into 10, that is equal to root of 4000 square plus 3000 square. Therefore, from this equation, we can get it as the MA equal to modulation index, amplitude modulation index, which is the ratio of the maximum value of the reference or modulating signal, sinusoidal maximum value, that divided by the maximum value of the triangular signal, which is equal to 0.47. Now let us see the 7th problem of 2022 gate question that also carry 2 marks. The steady state current flowing through the inductor of a DC to DC buck boost converter is given in the figure below. That is, this is the current that is shown here. And if peak to peak ripple voltage in the output capacitor is 1 volt. This is the buck boost converter. The peak to peak voltage of the voltage across the capacitor is 1 volt. then what is the value of this output capacitor? What should be the value? That is in microfarad. That is to be round off to the nearest integer. Therefore, this is the buck boost converter circuit diagram, the input voltage, and here the switch is there, and there's an inductor, and of course the diode is there, and the capacitor is there. Here we are getting the voltage polarity with the plus here and minus here. For the voltage inversion is there. Of course, the current, if you see that one, when switch is on here, the voltage across the switch is having a plus here and minus here. Therefore, we are getting a positive voltage. Current will be building up like this one. And when switch is off here, then here the voltage will become, of course, minus V0. Therefore, negative voltage across the inductor comes. Therefore, of course, VL equal to L di by dt. Therefore, since VL equal to negative, di by dt will be negative. That is the voltage, the current through the inductor is decaying. Therefore, this is during the on period of the switch and the current inductor current, and this is the off period of the switch. And the on period is given as, from this diagram, it's clear that it is equal to, it is given as, of course, 20, and out the off period is given as 30 as such. And here, that unit is given here. Therefore, the ratio of that, to find out the duty ratio, the total duty, the ratio is meant on period divided by the total time period. Therefore, it is equal to 20 divided by 50. 20 into, that is microsecond. 20 microsecond is on period and 30 microsecond is off period. The total time period equal to 20 plus 30, 50 microsecond. Therefore, the duty ratio of this one, the switch, is equal to 20 into 10 raised to minus 6 divided by 50 into 10 raised to minus 6, which is equal to 2 by 5, which is equal to 0.4. So the duty ratio D is given, is being calculated as 0.4. Then switching frequency is here. The frequency, if you see, watch here. What is the switching frequency? Switching frequency, this is 20 and this is 30. The total time period is given by 50 microseconds. Therefore, time frequency is given by 1 by t, or 1 by 50 into 10 raised to minus 6. That is equal to 20 kilohertz. So that's the switching frequency. Next step is that you have to calculate what is the average current through the inductor. What is the average current through the inductor? And find out the average current through the inductor. When switch is on, this is the current waveform. Voltage current is building up. And from here, minimum value of here 12 to maximum value 16. And when switch is off here, then the voltage across, this is off. Here the voltage across will be, across the inductor will be minus the output voltage V0. And then since the voltage is negative, the current is having a negative slope with this one. Therefore, this is the inductor current that is changing from the maximum value of 16 amperes to the 12 amperes. Now, question is that what is the average value of the inductor current? Now, to find out the average value of the inductor current, that is average value of the inductor current, we can find out that one. One method is that here, find out the total area under this one and you distribute between these two. That is the method of finding out the average value. Now, for the total area, you know, to calculate here. So once again, here, this is the triangle. Therefore, this area is nothing but half BH, half into, this is the time period, half into T into, and the height is equal to IL max minus IL minimum. And plus this is also to be added, which is equal to, again, this is equal to T and this is equal to IL minimum. Therefore, IL minimum into T. Therefore, this area and this area both are added, and that is distributed over this period, time period T, that divided by T. Therefore, if you calculate, if you substitute in this one, we get T gets cancelled, and here it will become IL max plus IL minimum divided by 2. It will become, here it is equal to IL max plus IL minimum divided by 2, which is equal to 16 plus 12 divided by 2, which is equal to 14 amperes. Therefore, the average value of the inductor current is equal to 14 amperes. Now continuing the same problem, here we found out what's average value of the inductor current, 14 amperes we got it. Next thing is that we have to find out average source current or average switch current, both are same. And to find out the average switch current or source current, we know that when switch is on, the inductor will be coming across the source, and then inductor current same as the switch current. Therefore, this is the, of course, the inductor current. Assume that switch current is having the same as the inductor current when switch is on. When switch is off here, the path is like this. Here the current is like this flows, but this is broken. Therefore, the input current is equal to 0 or switch current equal to 0. Therefore, input current equal to 0, switch current equal to 0. Therefore, this is the waveform. This is the waveform Actually, this is to be started from here only. This is the waveform corresponding to the switch current. Therefore, in order to find out the average value of the switch current or average value of the source current, again you have to find out what is the area under this one that is to be distributed over this time period, over the time period. Therefore, in order to calculate that one, average source current equal to half into, that is available only T on period, T on into IL max minus IL minimum, that is this area, plus again the minimum value of the current is there. That minimum value of the current is calculated as IL minimum into the on period, IL minimum into on period. Therefore, this is the total area, that is starting from here. This area equal to IL minimum into T on period. Therefore, that is the total area that is to be distributed over the total time period, that is divided by T. Therefore, that is the average value of the switch current or average value of the source current. Therefore, if you again, but T on is, as you know, that D times time period, dt. Substituting that one here, dt and dt here, and then we'll be getting it is equal to D into IL max plus IL minimum divided by 2, or meaning that it is equal to D times the average inductor current. Therefore, the source current is given by, or the switch current is given by, in a buck boost converter, D times the average inductor current. That is the derived. Of course, we have already found out the average inductor current as 14 amperes. Therefore, the average source current is equivalent by D into, that is 0.4 into 14, which is equal to 5.6 amperes. Therefore, that is the average current through the switch, or that average source current. Once you get average source current, and let us see the average output current we have to derive. What is the average output current? Average source current we have already calculated. D also E naught. Then you can calculate what is the average output current. And average output current and average source current, input current, are related as, in a buck boost converter, it is equal to 1 minus D divided by D. I0 divided by S equal to 1 minus D divided by D. Or we can say that I0 equal to IS into 1 minus D divided by D, or 5.6 into 1 minus 0.4 divided by 0.4, which is equal to 8.4 amperes. Therefore, the average current through the load I0 is given by I naught equal to 8.4 amperes. And we have already given that the ripple voltage at the output equal to, already it is given as 1 volt. And the basic relation to design the capacitor of a buck boost converter, it is equal to delta VC is equal to D I naught divided by F into C. This is to be remembered. This equation is to be remembered. D I naught divided by FC is the delta VC. Therefore, 1 volt it is already given. D also you know it, and we already calculated I naught. Now only F is also known. Only the unknown is capacitor C. For C equal to D I naught divided by F into delta VC. Substituting that one, D equal to 0.4, and I naught we calculate as average output current equal to 8.4 amperes, and frequency is equal to 20 kilohertz, and the ripple voltage at the output, this is equal to 1 volt. Substituting that one, we get it is equal to 0.168 into 10 raised to minus 3, which is equal to 168 microfarad. It is equal to 168 microfarad. So the inductor current is same as the source current. That is inductor current and source current. That is, that is plotted. That is just to plot. This is actually, this has to come here. Inductor current. This is the inductor current, and that is other one is the source current. That is, this is the source current or switch current. I'm explaining certain relation for the different types of converters like buck converter, boost converter, and buck boost converter. And average inductor current, that is average inductor current equal IL average is given by, this is a load current. I0 is the average load current. It is same as the average load current in the case of buck converter. And this is the buck converter configuration. Average inductor current is same as the average load current. And for a the average switch current, in this case average switch current is given by, that is, since the switch is at the input side, here the current is flowing in both, when switch is here, when switch is in on, and average switch current is given by the source current, that is IS. It is a when same switch current is same as the average source current. And voltage relation, that is V0 by Vd equal to D, or V0 equal to D times the source voltage. And current relation is that I0 by IS, average output voltage, output current to the input current. That is I0 by IS equal to 1 by D. And this is the circuit diagram of a buck converter. Coming to the boost converter, the average inductor current is given by the, because here this is the boost converter, this is the boost converter as such. Here average inductor current, that is average inductor current equal to the source current Is, because that is in series to that the input side. I mean, that is why Is. And the average switch current is here, it is equal to D times, I mean here D times Is. Now the voltage ratio relationship, that is V0 by Vs, that is average output voltage divided by the average input voltage, source voltage, which is equal to 1 by 1 minus D. And the current, corresponding current relation I0 by Is equal to 1 minus D. And this is the circuit diagram of a boost converter. For a buck boost converter, the corresponding average inductor current or average current at the inductor current is given by Is by D, that is source current, or Is equal to D times, I mean average inductor current. And average switch current is given by the source current, same as the source current Is. And the basic relation for the output voltage and input voltage, average output voltage and average source voltage or input voltage equal to D by 1 minus D. Of course, the polarity will be reversed if the output polarity is opposite to the input voltage. And the current relation is that 1 minus D divided by D. So this is the circuit diagram of a buck boost converter. So remember this one relations, and I0 is the average output current, and Is is the average source current or input current, and D is the duty ratio, which is equal to on period divided by total time period Ts, and T is the, this is this is for a this is in the continuous conduction mode, CCM mode. These are the relations are for continuous conduction mode.